Well, dear students, this is 11th lecture in the series of mechanics of metal forming, and since we have already covered the state of stresses chapter fully, let us see some of the things and then we would be solving some of the tutorial problems covering different aspects of state of stresses and all that. So, look at this figure where the equilibrium of forces has been shown over a given volume. The volume V is taken of some body, and if we take a small area over the surface of this volume ds, so on this particular surface area, let us take Nj as the normal and Ui represents the component of vector u, which is associated with an elemental area ds of a closed volume V. So the components of normal vector Nj, that is the unit normal vector, which is directed along the outside normal to the area ds, has been shown here, the above figure. And if we use the divergence theorem, that means but earlier equation, if you recall, so one can write down that over the volume the summation of these three components, which has been shown here. So that means over the volume deva sigma ij by deva xj directions multiplied by dv plus over the volume gi dv minus over the volume density multiplied by ai dv, and that these sums should be equal to 0. So for any infinitesimally small volume, particularly this volume will reduce to this particular above equation is after if you apply the divergence theorem. So it reduces to deva sigma ij by deva sigma xj deva xj, that is the xj is 1 2 3 j plus gi and minus density ai is equal to 0. So when the body forces and acceleration component or inertia forces are negligible, this particular equation, which is a general equation of equilibrium, will reduce to the already derived stress equation, if you recall back. So starting with that, now let us take out some of the problems. So let us take the problem number 1 as shown here in this figure number 1, rather figure number 2, where a point has been shown. If you look at this figure, which is a kind of cantilever. So the component of the stress tensor, that is sigma, at point P of the beam, which is shown here in the figure, with respect to xyz coordinate system, and the components of the stress tensor is given to you. So that means it is given as 35 minus 25 0, minus 25, minus 15, 0 and 0, 0, 1 megapascal. So this is what the elements of the stress tensor. So let us find out A as the stress vector, which is Tn on the plane whose normal is given as normal vector, which is given by 1 by root 3 and multiplied by unit normal along I x y z, that is I plus j plus k. So this we have to calculate and find the normal, therefore that means sigma n, and similarly the shear stress, normal stress and shear stress component of the stress vector, that is Tn. And secondly, the part B, we have to find the component of the stress with respect to rotated coordinate system. When it is x y z is rotated to x prime y prime z prime, then what will happen, the unit vector which was earlier I j k will be rotated to I prime j prime k prime along x prime y prime z prime axis, and this has been shown as I is equal to 0.6 I plus 0.8 k, whereas j is equal to j and the k vector is given as minus 0.8 I plus 0.6 k. So let us solve this problem using the concept of the state of stresses. So recall the point P is shown here in this figure, and in the beam on both the front view as well as the left side view. So the corresponding width, height and length of the beam is already shown in this figure. So how to solve? So we can use Cauchy relations in array form to evaluate the stress vector, that is Tn. So as per equation, if you recall back, this particular equation which is given here, we denote its component with respect to xyz coordinate system by, that means Tnx, Tny and Tnz. Further, the given components of the unit normal, therefore that means n cup can be written as that is nx, ny and z, and that is nothing but 1 by root 3. So writing the components of that is the normal the stress tensor, that is the stress tensor component of the stress tensor in the array form using the previous equation, we can then one can write down that is there is a matrix consisting of column matrix, that is Tnx, Tny and Tnz, and on left hand right hand side the multiplication of 2, that is 1 is the stress vector that is given and multiplied by the another column vector which is the components having 1 by root 3, 1 by root 3, 1 by root 3. If you multiply this, it comes out to be 10 by root 3, then minus 40 by root 3 and 0. So thus the stress vector can be now written as Tn, which is equal to 10 by root 3 I minus 40 by root 3 j megapascal. So this is what's the solution number 1, and using the previous equation, this particular equation, we get the normal component therefore of the stress vector as, that means sigma n, that is Tn multiplied by Ni. So that can be further expanded, and this is the tensor notation. So 10 by root 3 multiplied by 1 by root 3 plus 40 by root 3 multiplied by 1 by root 3 plus 10 multiplied by 1 by root 3, and then if you evaluate it comes out to be minus 10 megapascal. So further using this particular equation which is shown below, we get the magnitude of the shear component of the stress. So just by transferring the left hand side to the right hand side to the left, one can find out the magnitude of the shear component, that is sigma s mod, which is equal to Tn square minus sigma s square and whole raised to the power under root. So that if we evaluate, it comes out to be as shown here 10 root 14 divided by root 3 megapascal. So this is what's the answer as has been asked to find the magnitude of the shear component of the stress vector. So that has been done. Secondly, to find the components of the stress with respect to x prime, y prime, z prime, that is the rotated coordinate system, we have to first calculate the transformation matrix Q, as you recall, and then one can get the direction cosines of the unit vector, that is ijk, from the equation, this particular equation, and substituting these in the equation, the earlier equation, we can get the expression for Q as like here, which is the components where it is given as that is the 0.6, 0.8, 0.10 and minus 0.8, 0.6. So using the tensor transformation relation like the equation which is shown here, one can get the following matrix of the component of the stress tensor with respect to the rotated coordinate system, that is x prime, y prime, z prime. That means the stress vector can be now be written as vector q multiplied by the stress vector in the rotated coordinate system, it is being said. So it becomes equal to transformation matrix Q multiplied by the stress vector which has been shown above and multiplied by the transpose of the transformation matrix Q. So if you multiply these three matrices, one can get the component like here 12.6 minus 15 minus 16.8 and then minus 15 minus 15 20 and minus 16.8 20 and 22.4 respectively, and this is what is in megapascal. So this particular equation, which is observed by obtained by multiplying these three matrices, shows that the matrix of stress is symmetric with respect to the coordinate system, the change coordinate system x prime, y prime, z prime as well. So note here that the stress component, that is sigma xz, sigma yz and sigma zz are 0 at point P of the beam. Such a state is called therefore as the state of plane stress at a point in xy plane. When these stress components are 0 at every point of the body, and if additionally the remaining stress component, that is sigma xx, sigma yy and sigma xy are independent of coordinate z coordinate, it is called as state of plane stress. Okay. So, in the body, in a body, and particularly in xy plane. So, it can be shown that the state of stress in the beam of the particular figure which was given of this type is okay, and that is whatever has been proved in the part B is proved now. Let us take another problem here where the components of the stress tensor sigma is given at a point and with respect to the xyz coordinate system. It is shown here the components, and let us find out six things. Number A as the principal invariant of this particular stress sigma, then find the principal stress, that is sigma I, and the unit vector along the I directions, that is 1 2 3, along the principal directions, and therefore arrange the sigma I such that sigma 1 is greater than sigma 2 and is greater than sigma 3, and further choose the scene of the unit vector such that it is in direction 1 to 1 direction 1 dot 2 and then cross product with 3 becomes plus 1. And the third part C, let us find the maximum shear stress, that is the mod of the sigma I max and the normal to the plane on which this sigma acts. So, and then express the normal in terms of the unit vectors, that is ijk. And the D part, let us find out the octahedral normal stress, that is sigma oct, and the corresponding shear octahedral shear stress. And the last one, the E, let us find the hydrostatic and deviatoric part of the total stress vector which is given earlier. So, how to proceed? So, one can proceed in a very simple manner, like if you substitute the value of that is the component of this stress tensor sigma ij from the previous equation, that is and the values of the permutations symbol, if we say the epsilon ijk from the previous definition, one can write therefore that the first invariant, one can calculate the first, second and third invariant. So, first invariant will be what? That is I, first invariant I, and that is what is sigma I11, that is the value, and that can be 18 plus 32 plus minus 20, and that comes out to be 30 megapascal. Then second invariant can be as the tensor form 1 by 2 sigma ij minus sigma ij. This is what the equation. So, if we expand and if we substitute the value of this component from the stress tensor given components of the stress tensor, one can find out, and it comes out to be 1000 megapascal square. And similarly, the third stress tensor can be found out, that is epsilon ijk and sigma ii, sigma then 2j and sigma 3k. If we substitute all these things in a long component which is shown here in this particular equation, and particularly this equation is a long equation which is given. So, one can find out the value, and if you substitute all this results into 0 megapascal. So, this is what the answer A. Then if we substitute for the answer B, let us try. So you substitute the values of the first invariant, second invariant and third invariant from whatever has been observed in the part A in this particular cubic equation which is given here. So if you just substitute, we get this particular equation, and therefore the roots of this equation is that is lambda is 0, minus 20 and 50. So arranging them in decreasing order, we get the following values of the principal stresses. Therefore, so that means we get sigma 1 as 50 megapascal, sigma 2 as 0 megapascal and sigma 3 as 20 megapascal. So that is the solution, and to find the unit vector which has been asked, that means along the principal directions 1, 2, 3, one can use this particular equation. So this equation, let the unit vector along the first principal direction be this one which is shown here in equations. So that is the component of the 3 directions, and if we take I is equal to 1, so this particular equation becomes in the format of the matrix equation. So the matrix equation on the left hand side, where we have the stress matrix, then the unit vector matrix, and on the other side it is the matrix corresponding all 0 component as the equation earlier. So the stress matrix, the diagonal terms as are common, sigma 1 1 minus sigma 1, sigma 2 2 minus sigma 1, sigma 3 3 minus sigma 1, and all other components are as usual. So if we take this and if we substitute sigma 1 as 50, that we have already found it calculated, and the value of sigma ij from the previous, the value which is given, and if we expand the above equation, one can find this equation. So the set of 3 equations, as the first is 18 minus 50 multiplied by the first the principal direction plus 24 second principal direction along y plus third principal direction which is equal to 0, and likewise. So from these 3 equations corresponding to 3 directions, the third equation one can obtain by putting it as equal to 0, the direction values. Note that the first 2 equations are linearly independent, linearly dependent, and each of them gives the value which is 4 by 3 and multiplied by the corresponding direction. And because this is a unit, this term defines the unit vector, so one can write down that the vector in direction 1 x y z, that is the unit square of this thing is 1. So substituting that the vector along first direction in z is 0, and along the y direction it is 4 by 3 as evaluated earlier. So in the above equation one can obtain the value which is for the which is equal to plus minus 3 by 5, and choosing the positive sign one can have this particular expression for the unit vector along the first principal direction which has been asked. So it becomes, along the first principal direction, unit vector becomes 3 by 5 I plus 4 by 3 j, and similarly one can get the expression for unit vector along the other 2 principal direction, that is y and z as well. So like here, which is already shown here, so like the third principal direction, it is simply minus k. Note that the where the sense of the second unit vector has been chosen to be arbitrary, that that of the third one has been selected to as to satisfy the condition, that is the summation of that means dot product and multiplied by the cross product with the third direction, it should be equal to plus 1. So, this is what the second answer. And then to start with the third, the maximum shear stress, because it is given by the equation which is shown here. So, if you substitute the value of sigma 1 and sigma 3 from the previous one, and in this equation, that is the sigma 1 max, so one can find out sigma 1 minus sigma 3 by 2, and that is what it gives 35 megapascal. So, the normal, that is n kappa n cap rather, to the plane on which the stress, that is the shear stress, maximum shear stress acts, are given by this equation. And if you substitute the expression for the unit normal unit vectors in from the, one can find out the expression for normal vector, and which is shown here, and it is equal to 1 by root 2 multiplied by 3 by 5 I plus 4 by 5 j plus minus plus k vectors. So, this is what the part C answer. Then for the D, we have where we have to calculate the octahedral normal stress and shear stress. So, one can use the equations related equation, and if you substitute the value of, that means the first and second invariant from the previously that we have already calculated. So, the octahedral stress becomes first invariant by 3, and that comes out to be 10 megapascal, and similarly the shear octahedral shear stress can be calculated as 2 by 9 first invariant square plus 3 times of the second invariant, and whole to the power 1 by 2, and when we evaluate, one can get 10 under root 78 by 3 megapascal, and that was the answer for the part D. For the answer to the E, as per earlier equation which is shown here, the components of the hydrostatic part, it can be calculated just simply by 1 by 3 sigma II and multiplied by chronicle Ij delta. So, because sigma II is given as 30 from the previous equation, the matrix of the hydrostatic part of the stress can be calculated as this one which is shown here. So, the diagonal elements are 10 10 10 and all other elements are 0, and that is how it shows the hydrostatic part. Now, if we use sigma II as 30 and this equation, the components of the deviatoric part can also be obtained. So, the deviatoric parts can be directly obtained from the total part, that is the sigma II minus 10 multiplied by chronicle delta Ij, and using the values of sigma Ij from the equations which was given in the very beginning, the stress vector tensor, one can get the proper equation which is here. So, the deviatoric component is nothing but the multiplication of the 3 such matrices which is shown here, and that comes out to be in megapascal. So, this particular equation is shown here as a. So, in the state of stress, which is given by the equation in the firstly it is given is not 0 therefore. So therefore it is not a state of plane stress at a point. So in case of xy plane, okay. So however, since the principal stress sigma 2 is 0, it is the state of pure it is a state of plane stress at a point in the plane perpendicular to the principal direction 2, and therefore this is the what we wanted to calculate, the last part of the answer. Let us take another problem where the stress at a point is given by this particular stress tensor, where it is the elements are 5 3 2, 3 10 4 and 2 4 6. So let us find out the normal and shear stress component at a plane which is equally inclined to the 3 axis, and the unit of the stresses in Newton mm square. Let us find this out. So how to start with this? How to start? So if you recall back, can we try? So the direction cosines of the normal to the plane which is equally inclined to the 3 axis can be calculated. How much it would be? Because it is equally inclined, so it makes equal angle. So what would be the direction cosines if it is taken as LMN? So all would be equal, and that is would be equal to 1 by root 3. So the normal stress can be calculated. That means normal stress would be equal to simply sigma ij multiplied by ni nj, and if you substitute the component of the stress tensor from the which is given and the value of the direction cosines and then the normal to the plane, if you calculate, so it comes out to be 13 Newton mm square. So the components, that is the total stress component along 1 and 2 and 3 vector of can be then found out. So that means the first component of the stress can be calculated as, that is sigma I1 sigma nj, and that would be what? It would be equal to sigma 1i ni plus sigma 2i n2 plus sigma I1 n1, because it is along the first one. So that comes out to be 5 by root 3 plus 3 by root 3 plus 2 by root 3, and that comes to be 10 divided by root 3 Newton mm square. And similarly one can also find out the other component, that is second and third, which comes out to be 17 root 3 Newton mm square and 12 root 3 mm square, and therefore the square of this would be 100 plus 289 plus 144 divided by 3, and that is what is given as 533 by 3, and therefore the stress can be calculated as, that is the shear stress can be calculated as, that means what is 533 by 3 minus 169 and under root, that is 2.94 n Newton mm square. So that's the solution. So let us try with this problem also, where we have this particular problem number 5. So where the stress at a point is given by the 3 principal stresses, that is 100, 120 and 200 nm, that is Newton per mm square. So we have to find out the shear and normal stress on a plane which has normal with direction cosines as 1 by root 3, 1 by root 1 by root 2, 1 by root 2 and 0. So if we try this, so how to proceed? So again let us recall. If you recall the components of the above stress states, what would be? That means components are sigma 11, sigma 22 and sigma 33, and it is already given. So that is given as 100, 120 and 200 and Newton mm square. So while the other component are all equal to 0, so the normal stress on the inclined plane can be simply calculated as what? That is the summation of these three in terms of the multiplied by there than the unit normal. So that means it is the summation of sigma 11 and n1 square plus sigma 22 n2 square plus sigma 33 n3 square. If you substitute this, that comes out to be 110 Newton per mm square. And similarly the shear stress can be calculated. That means the shear component as S1, S2 and S3 can be calculated if it is taken as the notation. So that would be simply sigma 11 N1 plus sigma 21 N2 plus sigma 31 N3. That comes out to be 100 root 2. And similarly the first component that is the normal and the shear, along the shear one the can be calculated as your 1 by 20 root 2, and that is what is third is 0, and therefore the total stress would be your 110.45 Newton mm square, and the shear stress therefore that is the sigma S can be calculated simply by the total stress square minus the direct stress, that is the normal stress square whole raised to the power under root, and therefore it is 10 by root 10 Newton per mm square, and that's what's the answer. So then there is another next problem number 6. If we have the problem where the stress state at a point is given by the three principal stresses like sigma 1, sigma 2 and sigma 3, and let us find out the normal and shear stress on the octahedral plane now. The previously it is given as your on the plane which has a normal with the direction cosine as 1 by root 2, 1 by root 2 and 0, but here it is which is on the octahedral plane. So how to start with? We have already seen the octahedral stress, we calculated in one of the problem previously. So the octahedral plane is a plane, if you remember, which is inclined equally with all the directions of the three principal stresses. So direction cosines of the normal to this particular plane with respect to sigma 1, sigma 2 and sigma 3, that is the direct stresses along the stresses would be how much, because it is equally inclined, so it is 1 by root 3, 1 by root 3, 1 by root 3, and therefore the normal stress can be evaluated as your sigma n, and that is the summation of the, that is sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square. So where, and if you that becomes 1 by sigma 1 plus sigma 2 plus sigma 3 by root 3, because it is equally inclined. So the total stress along the component of the total stress, that is along 1 and 2 direction, can therefore be calculated as sigma 1 n1 is equal to sigma 1 by root 3, sigma 2 becomes sigma 2, that is the total stress along 2 directions, sigma 2 n2, and that is how one can calculate. And similarly, the shear stress on the this particular octahedral plane can be calculated as your which is sigma 1 square plus sigma 2 square plus sigma 3 square divided by 3 minus in bracket sigma 1 plus sigma 2 plus sigma 3 divided by 3 whole square, and this is what the bracket closes. So, and under root the whole to the whole, and this has been shown here in the problem. So, it may be then substituted here, and that becomes in fact the octahedral that is the shear stress on the octahedral plane, as if we take it out the component, so it becomes 1 by 3 and multiplied by the components in under root, and these inside under root there are 3 components. The first component is sigma 1 minus sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So, this is what the stresses on the octahedral plane. So, let us try once again with problem number 7 here, where it is a different, because here the stress state at a point is given, and the tensor stress tensor component is 10 4 0 4 12 0 and 0 0 0. So, let us find the principal stresses, and these stress components are in Newton mm square. So, how to proceed? If we recall back the equation which we derived, and particularly this equation, which is, so the principal stress can be are in fact the roots of the following equation, that means this one. So, if we use this equation and if we substitute the component here in the, and then one find it here, that means minus sigma and multiplied by the 3, that means 2 term. The first term is 10 minus sigma multiplied by 12 minus sigma and minus 16, and that is what is equal to 0. Or one can then say that is a sigma in bracket sigma square minus 22 sigma plus 104, and that is what is equal to 0. So, from the above it is clear that one of the principal stress, say where say the sigma 3, if it is 0, so for sigma 1 and sigma 2 one can evaluate the second factor from second factor to 0, that means it will become sigma square minus 22 sigma plus 104, and it is equal to 0. So, these gives 2 roots of the stress, and that what has been asked. So, that is the principal stresses sigma 1 and sigma 2, and that is 22 plus minus under root 22 square minus 416 divided by 2, and that gives your 11 plus minus under root 17 Newton mm square. So, this is what is the interesting problem. Let us take another problem number 8, where we have the components of the stress tensor which is given, and let us determine the principal stresses for the following the stress state. The stresses are, the components are in fact Newton mm square. So, how to start? Again, if we recall the equation, So if we substitute the equation there, we get in a similar manner a equation which is minus sigma multiplied by sigma square minus 100 and it is equal to 0. So one of the principal stress is because 0. So let us take this 0 is sigma 3 and the remaining two principal stresses, that is sigma 1 and sigma 2, can be calculated just like previously we have calculated as 10 mm and Newton per mm square and 10 Newton per mm square respectively. So this is what the variety of problems we have taken to illustrate the what we have done in the state of stresses. Let us take another very interesting problem, problem number 9, which is based on the Mohr circle determination, and that is also for the 3-dimensional Mohr circle construction. We have already seen the construction detail, how do we draw 2-dimensional Mohr stress circle as well as 3-dimensional. So let us take this problem where the state of stress at a point is given by the three principal stresses like 100, 70 and 30 Newton mm square. And let us construct the Mohr circle stress circle diagram and let us determine the normal and shear stress on a plane. The normal to which has the direction cosines as 1 by 2, 1 by root 2 and 1 by 2. And let us also verify and the result which we obtained graphically and determining the stresses by analytical as well. So that will give us the confidence. So how to start with? So to start with, let us see this figure. To help you, for helping you, let us consult this figure which is shown here. So the Mohr stress circle which is shown here, and how do we construct it? If you recall back, we take a radius that is O3E prime from the center O3 which is shown here at an angle which is 2 cos inverse 1 by 2, and that comes out to be 120 with respect to the horizontal axis, and with the O1 as the center and radius equal to the O1E prime, one can draw an arc to cut the circle with center O2 at F prime, and similarly from O1 take a radius O1C prime at an angle which is equal to 2 multiplied by cos inverse 1 root 2, and that is equal to 90 degree. Now with O2 as center and radius equal to O2C prime, draw an arc, that is C prime D prime, to cut the previous arc, that is F prime E prime, at the point P prime and the circle with radius O3 at point D prime. So from P prime one can draw P prime n which is perpendicular to sigma n axis. So if you look at this figure, so one can also calculate and one can also take, that is O2A prime at say at an angle O dash A dash R prime which is equal to 120. So the shear stress can be calculated as P prime n, and the normal stress can be measured from this plot as On. So this is what has been shown here. If you look at this figure, so it has been marked also the value of normal stress and the shear stress. It has been marked as 24.81. So by taking the measurements and multiplying by the scale, we find the stresses as normal stress as which is approximately 67.54 Newton per mm square, and the shear stress as 24.81 Newton mm square. And so this value can also be determined by substituting in the equation given below. So like the normal stress would be sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square as the equation. So if you substitute it, we get 100 by 4, 70 by 2, 30 by 4, and that is what is 67.5. And by graphically Mohr's stress circle we have found out 67.54. So it's absolutely okay. Similarly, the shear stress is calculated as sigma 1 n1 square plus sigma 2 n2 square plus sigma 3 n3 square, and that is what is equal to 5175, and that is also calculated as, that is the shear component, total stress minus sigma the normal stress square under root, and that comes out to be by the equation 24.87 Newton mm square. So and if you compare it with the graphical solution by Mohr's diagram, that comes out to be 24.81. So it is again very close, and this verifies that the Mohr's diagram is okay. It is absolutely well. It is easier to draw and easier to measure it and directly use it. So with this exercises, you can it gives strength. One can solve many more problems similarly, and one can practice to get more and more confidence. There are varieties we come across most often when we solve bigger problems in metal forming. So these exercises just to help you for evaluating the stress at a point. So thank you once again for keeping patience, and there may be some problems on based on this as the objective. You can check with the web, and I will thank you once again.